Hello everybody, welcome to Cloud on Air if you're just joining us, and welcome back if you've been with us before. We've got a lot more interesting sessions coming up, so please do stay with us, and please do make use of the advantage, or make advantage of the ability to ask questions down there. We love live questions, particularly really tricky ones, so please test us out and do fill in the surveys because we do want to know what you care about and what you want to see more of. Next up, we've got a really interesting session from Neil Markwick. So Neil used to work as a software engineer inside of Google using Google Spanner inside of Google, but now actually he's moved into the solution architecture team. And solution architecture team, he works with customers to help them to also take advantage of what Google Cloud Spanner can offer. So Neil's going to walk us through a little bit about the technology behind Google Cloud Spanner. I think it should be really, really interesting and looking forward to it. So over to Neil.
Good morning. So, as Tom said, I'm Neil Markwick. I'm here to talk to you about Cloud Spanner. So what is Cloud Spanner? It's the only enterprise-grade, globally distributed, and strongly consistent database service built specifically for the cloud, combining benefits of relational database structure with non-relational horizontal scale. It is unique in the marketplace in that it combines transactions, SQL queries, and relational structure with the scalability you typically associate with non-relational or NoSql databases. Cloud Spanner is part of Google Cloud's database and storage portfolio. The platform has a robust assortment of managed database and storage services that you can use to build applications from in-memory caching on the far left to enterprise data warehousing with BigQuery on the far right. We have cloud storage for binary or object storage and two non-relational database offerings in Cloud Data Store and Cloud Bigtable. We also have two relational database services with Cloud SQL, which can run MySQL and PostgreSQL, and Cloud Spanner. The goal with having so many choices is to provide you with a toolbox so that you can use the right tool for the job. Cloud Spanner sits in the relational section, but next to non-relational on this chart because it combines the relational semantics, schemas, enforced data types, and consistency guarantees that you would find in traditional relational databases with horizontal scale associated with non-relational NoSql databases, allowing you to have your cake and eat it too. Many other databases out there approximate aspects of what Cloud Spanner can do, but they don't quite get there. Comparing Cloud Spanner to our traditional managed relational database offering, you can clearly see that Cloud Spanner's performance starts where Cloud SQL's finishes. In addition, this performance is dynamically scalable. With only 4 mouse clicks or an API call, you can add more nodes to your database. These nodes will come in line in the order of minutes, so you can scale up to handle demand for peak periods, such as Black Friday sales for a retail store, and scale down again afterwards, reducing your long-term costs. No more needing to stop and restart your instance to add more CPU and RAM for performance. And in addition, you don't need to reshard your database when it's grown too big for a single instance. No maintenance windows, nor any planned downtime, and Cloud Spanner instances are automatically replicated across availability zones, meaning that it is always available. Cloud Spanner allows you to future-proof your backend with no need for rewrites and migrations, giving you a database that scales with your application. This is all fully managed for you with a 4 nines SLA or 5 nines SLA, depending on if you're running the regional or multi-regional configurations. So, how did Cloud Spanner come to be? Well, back in 2005, Google was significantly smaller with about 1/10 of the employees and 1/20 of revenue, but growing extremely quickly. There was no database product on the market that could handle their requirements. For example, all AdWords transactions, that's the details of every advert shown and clicked on, every dollar of revenue, was stored in a massively complex sharded set of MySQL databases. Every second of downtime cost significant revenue, and resharding was a nightmare process that took multiple years to complete. What did Google need? We were dealing with monetary transactions, so we needed global consistency and no data loss. We needed it to be highly available. Every minute of outage is equivalent to millions of dollars in lost revenue. We needed automatic sharding with no downtime and low latency. We needed a database that can go into trillions of rows with constant growth. AdWords was growing quickly from a $10 million a year business to over a $1 billion per year. And we needed something running on Google's existing private cloud infrastructure. So Google's engineers did what they often did, and invent something new. They created a new planetary scale database called Spanner, initially as a key value data store, but evolving over time into something more like a traditional database with schemas, tables, indexes, and the ability to perform complex SQL queries. This has been battle tested in Google at massive scale for more than 5 years, running services like AdWords, Google Play, Gmail. In fact, any Google project needing a consistent data store now uses Spanner. Since May 2017, we've made it available as part of Google Cloud Platform as Cloud Spanner. Cloud Spanner comes in two flavors: regional instances, where 3 read-write replicas are maintained in different availability zones within a single region. Each replica contains a full database copy, so that if there's a single zone failure, your database remains available with a 4.9's SLA. Your data is geolocated in this region, and for best performance, the compute workloads should also be in the same region. We have regional instances available in the central and eastern USA, Belgium, Mumbai, Taiwan, and Japan. We also have our most multi-regional offering, available since November 2017, where multiple read-write replica exist in multiple regions, adding another 9 to give a 5.9's SLA, or 5 minutes max downtime per year. There are 2 multi-regional flavors: NEM3 with 2 read-write replicas in the eastern USA, and the global multi-regional instance where 2 read-write replicas are maintained in central and eastern USA and 2 read-only replicas are maintained in Belgium and Hong Kong. So that was a high-level overview of what Cloud Spanner can do. Before diving deeper into how Cloud Spanner managed to achieve all this, let's step back a little and review some database theory. Back in the 1970s, Jim Gray started developing a database principle which is expanded upon by Reuter and Harder in the 80s to create the now well-known ACID algorithm to describe distributed databases. To recap, this means that a database transaction must have atomicity, all or nothing, consistency, no half-completed transactions should be visible, isolation, concurrent transactions should have effects no different than if they were performed sequentially, and durability. Once complete, the transaction persists even in the case of hardware or power failure. ACID databases force consistency. They guarantee that you're always reading the latest data and no data loss can occur, which often means that rows are globally locked during write, limiting the performance. The BASE acronym was coined by Dan Pritchett in 2008, somebody who is obviously not afraid of chemical puns, to be the opposite of ACID for distributed databases. This states that the database should be basically available. A response to a request will always be given, but no guarantees are given whether the data is consistent or even up to date. Soft state, the data state can change even while no transactions are currently occurring. These changes being caused by the E, which is eventual consistency. The data changes written to one node will propagate over time to all other nodes. Base databases, which are most NoSql databases, allow massive horizontal scaling, as there is no need to perform row locking on all nodes and no need to ensure the consistency of every transaction on every node. Thus, reads and writes can occur in parallel, increasing performance. But, and a big but, this only suits certain types of application, ones which must not care about data consistency, and often the application may be significantly more complex to handle possible inconsistencies. This brings us to the CAP theorem, created by Eric Brewer in 1998. Eric now works for Google Cloud, but not on Cloud Spanner. This states that it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees. Consistency, you have the same view of all your data from all nodes of the data stores. Availability, your data store always returns a valid response to requests and you'll always be able to read and write. And partition tolerance, your data store can continue operating if a network connection between nodes is broken or delayed. In practice, it is impossible to avoid partitioning in any network system, so you're left with 2 choices. NoSql databases are highly available and partition tolerant, but sacrifice absolute consistency for eventual consistency. The isolated nodes have to catch up with data written to other nodes when the network recovers. Traditional ACID database sacrifice availability to preserve consistency. Should a partition occur, the database simply stops being available and all requests will return errors. So, does Cloud Spanner break the CAP theorem? Remember that CAP is a theorem, not a rule, originally proposed to make designers think about the trade-offs involved. The caveats are you only need to forfeit A or C during an actual network partition, and that the A refers to 100% availability, which for a variety of reasons is effectively impossible. Cloud Spanner claims consistency and high availability. Does that mean that it is a CA system and does not care about P? Technically, no, as it is impossible for a distributed data store to magically transfer data from node to node when the network is down. In the case of a full network partition, Cloud Spanner will always choose consistency over availability. So technically, it is a CP system just like other traditional databases. But the actual availability of Cloud Spanner is sufficiently high that the users writing the client applications never have to worry about coping with the database returning read or write errors. Google achieves this high availability by minimizing the chance and effect of network partitions. So if a partition never occurs, Cloud Spanner is effectively CA. So the question then becomes, how does Google minimize P? Google has its own private global network. Cloud Spanner's internode data packets do not travel over the public internet over Google-controlled routers and links, both of which have high levels of redundancy of both equipment and paths, quality of service enforcement for data packets, and constant monitoring. For example, each data center has at least 3 independent fiber connections to Google's backbone network, ensuring redundant paths between any pair of data centers. Thus, events like a fiber cut on one path of the backbone will not make any difference. Or a misconfigured route advertisement from an internet provider which diverts the entire internet to, well, to pick a recent example, Turkey, will have no effect on Google's internal network. Google has invested massively in its own fiber connections and is a stakeholder in several transoceanic fiber cables, some of which are listed here. The photo above is of the ship laying the faster fiber from the US to Japan and Taiwan. This cable went live in June 2016, providing 60 terabits of bandwidth, 10 terabits of which are private to Google. At the time, it was the highest capacity trans-Pacific cable, and it will only be beaten by another Google joint venture, the PLCN cable between the US and Hong Kong. This gives Google Cloud Platform the largest network backbone of any public cloud provider and allows Cloud Spanner to effectively ignore the possibility of network partitions. So what about the C, consistency? It usually requires significant cross-machine communication to give a guarantee of consistency, as all transactions have to be applied to all nodes sequentially, and on a global scale, the speed of light itself becomes a limiting factor. It takes a data packet at least 60 milliseconds to cross the Pacific Ocean, for instance. Cloud Spanner guarantees external consistency, which is the strongest level of consistency, meaning that the system behaves as if all transactions were executed sequentially, even though Cloud Spanner actually runs them across multiple servers. This requires that all nodes synchronize their state with each other, which again would normally be difficult across large distances. This is where another Google-developed technology, TrueTime, comes in. TrueTime is a way to synchronize clocks across multiple data centers. The system uses a combination of GPS and atomic clocks, each correcting for the failure modes of the other. GPS can have antenna or receiver failures, local interference, spoofing, and incorrect leap-second handling. Atomic clocks can fail in other ways, and over long periods of time can drift significantly due to frequency error. Combining the two sources, using multiple redundancy of course, gives an accurate source of time for all Google's applications. But clock drift on each individual machine can still occur, and even with a sync every 30 seconds, the difference between the server's clock and the reference clock can be as much as 2 milliseconds. This drift will look like the sawtooth graph on the right, with uncertainty increasing until corrected by a clock sync. 2 milliseconds in computing terms is quite a long duration, so TrueTime actually includes this uncertainty as part of its time signal. TrueTime quantifies the worst possible time drift between clocks in all data centers around the world compared to the global clock, with an average of plus or minus 2 milliseconds. When requesting the current time, TrueTime returns an interval containing 2 timestamps, T1 and T2, the difference between which is double the maximum drift. So now we have a time interval we are sure contains the global timestamp. We can use before and after comparisons on this interval on machines across the globe to verify if one TrueTime's timestamp occurs before or after another. Cloud Spanner assigns a timestamp to each and every read transaction, and because of TrueTime, a write transaction at a given time is guaranteed to reflect the result of all writes before that time, whilst a read transaction for data at a given time will require the reading node to have received all the updates until that time. This allows different Cloud Spanner nodes to make decisions about the order of transactional operations made from other nodes, often sometimes without any communication at all, simply by comparing these TrueTime timestamps. So Cloud Spanner does not break cap, it cheats. By minimizing the possibility of network partitions, the availability is kept high, the global timestamps allow fast data sync to preserve consistency, and the sharding of the database across multiple machines and zones means there is no single point of failure. So let's now have a look at how Cloud Spanner works internally. Here is a diagram of a 3-node regional Cloud Spanner instance, the minimum recommended configuration, hosting 2 databases. As you know, regions in GCP are independent geographic areas that consist of availability zones. Locations within regions tend to have round-trip network latencies of under 5 milliseconds at the 95th percentile. Zones should be considered a single failure domain within a region. So when a Cloud Spanner regional instance is created, compute and storage is allocated into all 3 availability zones, and the databases in that instance are fully replicated across all the zones. Note that the compute and the storage are also separated for additional reliability and redundancy. Each table in the database is broken into several what we call splits, using ranges of the primary key. For example, this table, which uses a simple monotonically increasing integer key, is separated into 9 splits using ranges of the key. In reality, the number of splits can vary according to the amount of data. For each split, a Paxos group is formed from the 3 replicas in the 3 zones. Paxos, by the way, is a set of protocols for agreeing on consensus amongst a set of processing instances. The Paxos group for each split determine among themselves which zone should be the leader and which zones should be replicas. The leader becomes responsible for write transactions, whilst the replicas can be used for simple bounded reads. In this example, for split 1, the split replica in zone 3 becomes the leader for the group, and in the case of failure of the leader, the consensus is redetermined and a new leader may be chosen. For different splits, different zones can become leaders, thus distributing the leadership roles amongst all the Cloud Spanner compute nodes. It is using this distributed mechanism of splits, leaders, and replicas that Cloud Spanner gains its both high availability and its scalability. Coming back to our table with 9 splits and its sequential integer key, you can see that a problem starts to occur if we append new rows at the end of the key range. These rows will always be added to the last split, so for a frequently appended table, this last split will have more activity than the others and will become a performance hotspot. The leader for this split will have significantly higher load than the others, and in addition, the split distribution will be unbalanced. For this reason, sequential integer keys, and for a similar reason, timestamp-based keys, are an anti-pattern in Cloud Spanner. Note that Cloud Spanner does perform load-based splitting. It adds split boundaries automatically when it detects high read or write load for keys in a single split, or when a split grows larger than a maximum size. It also rebalances the splits in the background. Given that highly deterministic keys are anti-pattern and can cause performance issues, what would be a good key? Well, anything where the high-order bits of the key are evenly distributed. This may be some real-world attributes of an object, for example, its lat-long position, or it could be a random ID, such as a UUID, but make sure that the UID is actually random and not deterministic on something like timestamp or MAC address, or by hashing a value. So, going back to our Cloud Spanner instances, how do read and writes actually work? Well, there are 2 types of read in the Cloud Spanner. Strong reads, where the absolute latest value needs to be read, and stale reads, where low read latency is more important than getting the latest values, so some data staleness is tolerated. In a strong read, the client wants the latest value, so the request is made with a true time value of now. The Cloud Spanner API identifies the split, looks up the Paxos group to use for the split, and routes the request to one of the replicas, usually in the same zone as the client. In this case, the request is sent to a replica in zone 1, so that replica requests from the leader if it is okay to read. It asks for the true time timestamp of the latest transaction on this row. The leader responds, and the replica compares the response with its own state. It sees that it's up to date, reads from its own storage, and returns as a result. In some cases, for example when the row has just been updated while the read request was in transit, the state of the replica is sufficiently up to date that it does not even need to ask the leader for the latest transaction. In this example, the replica has not yet received all the updates for the data being read, so when it asks the leader for the latest timestamp, the leader responds with a timestamp later than the replica's internal state. The replica then waits for the latest update, and once the transaction has been received, the latest version of the data is read and returned. In a stale read, the client does not request the absolute latest version of the data, just the data that is most recent, say up to 15 seconds old. The replica, in most cases, can simply return the data without even querying the leader as its internal state, but to show that the data is sufficiently up to date. You can see that in each of these read requests, no row locking was required. The ability for any node to respond to reads is what makes Cloud Spanner so fast and scalable. Now let's look at data writes. For example, a single row write. As before, the Cloud Spanner API identifies the split, looks up the Paxos group to use for the split, and routes the write request directly to the leader. The leader then locks the row, writes the data to its own replica, and informs the replicas in other zones of the update. The leader waits for write acknowledgements from the other replicas, at which point it unlocks a row and returns a successful result. With a multi-row write, the rows being written may be in many different splits or to different tables. So there may be different leaders. For example, splits 1 and 2 here have leaders in 2 separate zones. This is where things get a little more complicated, so I'll simplify the diagram a little. In this case, the client looks up leaders for all the rows needing to be written and informs them of the intention to write. These leaders are now known as participants in the write transaction. One participant is elected, again using Paxos as the transaction controller. It will be responsible for the atomicity of the transaction. In this case, Zone 3 is elected as coordinator. All participants acquire locks on their rows, this being the first phase of a 2-phase commit. If it is possible that locks cannot be acquired, such as in the case of a deadlock which Cloud Spanner detects automatically, the transaction is aborted and the client may choose to retry. The locks are replicated to the other zones. This is to allow for transaction failover if a participant or a leader is lost. The participants report back to the coordinator that all locks are required. When the coordinator sees that all locks are obtained, it initiates the commit, marks the transaction with the current timestamp. The commit is then written and replicated to the other participant leaders, and those leaders then replicate to all the other zones. Once everything is acknowledged and the locks are released, the coordinator can reply back with success to the client. So that was the situation with the regional instance. In multi-regional instances, such as this one, where one region in the US has a read-write replica and others in Asia have a read-only replica, writes from US clients will go directly to the local replica, and these updated data will be forwarded on to the read-only replica. However, writes from clients in Asia will be sent to the local Asia replica, who will forward the request via Google's backbone to the read-write instances in the US to actually perform the write. These instances in the US will then replicate the response back to the read-only instance in Asia, and then the response is returned to the client. Therefore, clients in Asia will have slightly higher latency on writes than in the US due to the transcontinental round-trip time. In a multi-regional read request, strong read operations to the read-write instance will occur in the same way as explained previously. However, a strong read to a request from the client in Asia will go to the read-only replica in Asia. As before in the regional instance, the Asia replica needs to request the latest timestamp from the leader, which will be in the US. So there is additional read latency to account for the Asia-US round trip, but the data is actually read from the local replica. In a stale or bounded read request, as before, the local replica is read directly, normally with no need for communication with the leader. So you can see in the multi-regional instances, writes in locations with read-only replicas are slightly slower, but reads are still fast, as data is read locally. So that explains why Spanner works under the hood. There are many market segments where Cloud Spanner can give improvements on existing database systems. Here are a few examples, but in general, Cloud Spanner simplifies application development by not having to deal with sharding and possibilities of inconsistencies, and enabling continuous growth. Any workload where transactional consistency is important can benefit from Cloud Spanner's availability and scalability. For some further reading, we have various white papers on Cloud Spanner's documentation site with the white papers for true time and the CAP theorem. We also have several customer testimonials on our Cloud Spanner homepage. For example, Marketo were impressed by the scalability and the possibility for global database instances to reduce latency for customers on the other side of the world. They were not able to find an equivalent product in other clouds. Quizlet were impressed by the power and scalability, and they published a detailed analysis of Cloud Spanner, comparing its performance to a 64-core MySQL instance. The analysis showed how Spanner continued to scale performance linearly with the addition of more nodes. And you can read this blog post with the detailed analysis at this link. So thank you for your time, and we'll break now and come back with your questions and speak to you shortly.
thank you very much.
Thank you.
That was awesome. I was geeking out. I hope everybody else was as well. We have a whole bunch of questions, actually.
Great.
So
let's see if they can stump me.
We'll see. So I guess to kick us off, you talked a little bit about time synchronization and true time.
Yeah.
Is that something based on NTP standard protocols, or is that something proprietary of our own? Can we comment?
Well,
or not?
As NTP only deals with an absolute time, true time deals with an interval. So NTP cannot, in that case, give us the right data. So we have our own protocol internally that we use to transfer true time data from the servers to the clients.
Cool, brilliant. And is that something that customers can make use of at the moment?
Not in the sense, but all our compute instance nodes are synchronized with true time, so their own timestamps are globally synchronized.
Cool.
But I don't believe that true time is available for our customers to use at the moment.
Okay, brilliant. So Spanner, big system storing lots of data in a transactional way. BigQuery, big system storing lots of data for doing analysis on. Both SQL. Talk us a little bit about the links between Spanner and BigQuery and how you can use the two together, for instance.
Yeah. So Spanner can be used for analytical purposes, but BigQuery is designed as a data lake to contain much more data. You can have petabytes of data stored in BigQuery, whereas Spanner it starts in the order of terabytes. So you'd have to have a lot of Spanner nodes to be able to handle petabytes of data, which can get quite expensive, and that's where BigQuery's cost benefits come in. So I believe we have a connector between BigQuery and Spanner, so you can export your Spanner data to BigQuery and query it that way. But as Spanner has a SQL interface, why would you do that? You can just perform your SQL queries directly on Spanner.
So is it kind of a trade-off between cost and performance and sort of non-functionals like that? Is that a fair way to sort of sum it up?
Indeed, yes. I mean, if you've got huge petabytes of data, BigQuery is obviously the way to go, unless you've got an infinite budget, which nobody really has.
We like infinite budgets, but yeah. Okay, brilliant. So how does Spanner know what kind of a read the client is asking for? Does that functionality have to be built into the client? Maybe, I guess more generally, how do you connect your code into Spanner? What's the API look like? What's the client like?
So we have a JDBC API, but this is for read-only, for connection to legacy applications. We do have our own APIs written in a variety of languages, in C#, in Java, in Node, in Python, and we have a REST API, so you can write any other language using the RESTful API. But to know which kind of read the client is asking for, this is up to the client to request it. So, for instance, if you were a bank and the customer wants to get their latest balance, you can tolerate a second or two of latency on that and provide the customer the latest balance. But if you wanted to get the latest balance to see whether the customer can take money out, then you want to perform a strong read and verify that the customer has got their money before they start removing it, because otherwise,
you're giving them money.
You're giving them money.
Yeah. Perfect. Okay, thank you. And does that obviously just imply that there are separate clients for each language as well as a RESTful backend API? Is that right?
There's a separate set of libraries for each language, yes.
Perfect, which presumably take care of a lot of the details
yes,
around
indeed.
actually.
Yeah. The APIs end up being as simple, like I want to read a row with the key value of X, and it returns then a data set with that value.
Perfect, thank you. I've been asked this one before. Are there any plans for a standalone simulator to test Spanner? Is the only way to test Spanner with Spanner, or is it
Indeed, yes. We do not have a mock instance of Spanner in memory equivalent to Spanner. We don't have anything like that. This is actually similar to other database engines like MySQL, which doesn't have a mock MySQL instance. You have to test your application on MySQL if you want to do an integration test. But given Spanner's scalability, for a test instance, you can create a single node database and run your application against that. However, what most applications do is they separate out their interface to Spanner into a separate library or separate block of code, and then they mock that. So that way you can simulate whatever Spanner gives you, and you don't have to worry about having a Spanner database running in the background containing your test data.
And I guess that would be true as a former software engineer. I guess that's generally true in terms of software development,
Indeed,
isn't it? In terms of mocking stuff out, it's quite common to create mock objects for unit testing and things like that.
Yeah, whenever you want to test something, you generally mock out all its interfaces, so you test it in isolation. You do, of course, have integration tests, but like I say, you can have a small Spanner instance for your integration tests, populate it, tear it down afterwards.
That makes sense. Thank you. So we talk about Spanner as being, it's a relational database, but it's got all the benefits of relational database, but it's also got all the benefits of infinite scale. Well,
hopefully,
yeah, largely limitless scale. But kind of joking aside, I mean, what about things like key constraints and foreign keys and things like that? Are the differences really between Spanner and relational databases, or is it almost completely identical?
Indeed. And we remember on my earlier slides, I showed that Spanner is in the relational database side, but close to the non-relational database side. So it has a lot of things which NoSql databases would normally, applications using NoSql database would normally have to do. So for instance, it does not have column constraints, it doesn't have foreign key constraints, nor does it have triggers. So this means that all your business logic has to be in your application layer, which is pretty much true for most applications anyway. So your application has to verify that the data is valid and correct before writing it to Spanner. And this, frankly, is best practices in a lot of applications out there in the world already.
So does Spanner support joins but not foreign key constraints?
That's
that
correct.
Right?
Yeah.
Okay.
So it does support joins. You can do inner outer joins. You can do select to struct. So you get in your results you get an array of structs from a subtable. But the actual key constraints is up to your application to verify that the keys used in one table refer to the keys used in another table.
Okay. Yeah. Okay. Is Spanner data secure?
Of course, is a simple answer.
Move on. No.
In Google Cloud Platform, all your data is secure.
Good.
We encrypt all data at rest, and we actually store the encryption keys away from where the data is stored to ensure that there's no chance of some nefarious actors getting hold of it. We also encrypt all data in transit between data centers. So that even if we're tapped by certain three-letter agencies, they would not be able to read your data as it transits between data centers. So it's up to your application, however, to deal with the security at the application layer.
Right. As is always going to be the way, of course.
Of course.
I mean, anyone can write an insecure application on top of a secure, yeah. And so does Spanner itself sit on top of other layers, or is it?
So it is its own thing. But it does sit on top of Google's basic storage layer, which is Colossus, which is something that other Google Cloud Platform storage services also use as the underlying data storage system.
So there's a lot of commonality around security baked into that, I
Exactly,
suppose.
yes.
Yeah. Okay, that's interesting.
All the replication and the encryption and the key management is handled by Colossus at the lower level. This is the same for Google Cloud Storage, for Google Cloud SQL's storage system as well.
I think we maybe touched on this a little bit already, but actually, so the APIs, I don't know if there's something to add. So I had the APIs provided in order to access and manage Spanner. I think maybe on the manage side, that might be a fair question, actually. We talked about access, but not managing. So
the management side, we have, of course, the Cloud Console, which gives you a nice GUI interface. You can go in there, you can say, how many nodes do I want? So I've got 3 nodes. Let's say I've got more power. I want 30 nodes. And you can just enter 30, click, indeed, and then wait a few minutes, literally a few minutes, for those nodes to come online. We also have the G-Cloud command line client, so you can run SQL statements in this command line client and get out text results. Similarly, we have a SQL interface in the Cloud Console, so you can enter a SQL statement into the Cloud Console, get the results, and also see the query plan, why your SQL statement took a lot of time, what it was doing, which tables it was reading, which index it was reading, so you can then optimize your indexes perhaps, or your SQL statement itself to make it more efficient. Finally, we have our APIs for reading and writing data to Spanner. But we also have APIs through RESTful interfaces for creating and destroying Spanner instances, creating and destroying Spanner databases, updating the schema, which I don't think I covered earlier. You can update the schema online, live, and it will become available over time. But again, this is a feature which is rarely available in other database platforms. So your Spanner instance can be controlled manually through the console or the command line client, or it can be controlled programmatically through the APIs, the libraries that we provide, and the RESTful API.
So actually, it's kind of just on that, when you do something like scale up and you add more nodes, how does things like distribution and sharding of the data work? Do you have to rebalance those nodes, or?
Well, magic, I think, is the word I need to use here.
We love magic.
So, as previously mentioned, the storage and the compute are actually separated in Spanner.
Right.
So no resharding actually has to occur. When you add more nodes, you're adding more compute. The Spanner recomputes the splits that are allocated. The Paxos groups revote amongst themselves and find out who's going to be the leaders. And then all your splits are shared amongst all your nodes, and everything just starts working magically as before.
Okay.
So there's nothing that you have to do manually once you add more power.
Okay, wow. And I guess that's also happening in the background as you're using it as well.
Indeed.
Things are rebalancing. I think you touched on this already, haven't you?
Indeed. Whilst if you add more data and your splits become unbalanced, Spanner will reshard the splits, move things around. This is happening automatically in the background, so it's something you never have to do yourself.
Brilliant. Cool. And we are getting questions as we speak. I'm frantically hitting the refresh button here. This is I think you'll like this one. How do you migrate from other RDMS systems to Spanner?
Well, this is actually a work in progress amongst the Cloud Spanner team.
Right.
So we do not have any automated procedures yet to migrate data. We do have a Cloud Dataflow connector to Spanner. So if you can get your data into Cloud Dataflow, Dataflow can perform the action of populating the data into Spanner using using a range of compute instances to spread the load. We do not have automatic migration tools yet, but as I mentioned earlier, there are some differences in the way Spanner manages things to a traditional database. For instance, the choice of key. If you had a monotonically increasing key in your existing database, that is kind of a bad idea if it's a frequently used table. Sure. So you might need to rework your application a little bit and change the way your keys are used. So you may need to do a little bit of data transformation to get benefits of Spanner's full performance.
Brilliant.
However, migration tools is something that we're working on. As I say, this is a fairly new product. It was only released last year, and the multi-regional was only released in November. So it's being developed all the time, and more features are coming out all the time.
Brilliant. So more questions just in. So is Spanner data encrypted at rest, and can you use user-supplied keys?
So yes, Spanner data is encrypted at rest, along with all data in the Google Cloud Platform. But we do not support user-defined keys. I'm not sure if I should say yet or not, because the way a DBMS works is the database management system itself needs to read the data. So user-defined keys, I'm not sure whether Spanner will eventually support that. That is something we'll just have to wait and see. But right now, it does not support user-defined keys. In the future, who knows? The future is a strange place.
Yes. I mean, generally speaking, adding support for customer-managed, customer-supplied keys across platform seems to be a trend.
It seems to be something happening, yes.
I mean, there are a
variety of customers that want to have...
we can comment on right now, I guess.
There are a variety of customers that want full control over their keys, and perhaps for regulatory purposes, they need to use their own keys. And more of our products are supporting user-defined keys over time, so we'll see what happens.
Cool. You mentioned data flowing between different regions. That's often something you have to pay for in the cloud. Is that something you have to pay for with
Cloud Spanner? No. So Cloud Spanner's multi-regional instances, the data flow between the regions is part of the costs of the Cloud Spanner platform. You do not have to pay anything extra on it. Similarly, if you do a query in the multi-regional, if you do a query from Asia, and that has to request the data from the US, the transport cost between the Asia instance and the US instance is included in the platform cost. It's not an extra multi-region egress-ingress cost. However, if you have a client in Asia, you do not have a replica in Asia, then of course you're going across to the US instance, and yes, there is a cost there. So if your clients are local to a replica, there is no additional networking cost.
That's interesting. Brilliant. I think that's pretty much it for questions. Thank you so much,
Thank
Neil.
you.
It's been an absolute pleasure. I hope people found that really interesting. I found it absolutely fascinating. And thank you so much for your time and knowledge, Neil.
Thank you, Tom.
Thank you.